Okay, hello again. Good morning. So we'll continue discussion with interfacing with C, and further touching on your LEA command or your LEA. This is for getting the address of uh something in the stack. Wait lang. Okay. Okay. So your LEA or your LEA is your load effective address command. This is for taking the address of a value. So for the stack, for example, we have EBP minus 4 as a stack. EBP minus 4 is the pointer. However, to get the address of that, we cannot simply say move EAX and then EBP minus 4. Because then that is an operation. It is not a constant. So your assembler would not be able to compile that. So instead, we use your LEA command or your LEA command. And to have a demonstration of that, we we will look at your ASMIO that assembly. So this is the include file, or yes, the compiled object file that interfaces with C. Now we use this for printing and taking input from the user. And this has one application of your LEA or least load effective address. But before that, we'll review some of the things that are here in your ASMIO that are related to interfacing with C. So let's check here. Because we are using Linux for this course instead of Microsoft or Borland, etc. We are using this command to compile this file, right? NASM, which is your assembler, -f elf -d, and then we have here elf type. This is define that we will look at later. So this is your build command, nasm-elf-d elf type. So take note of elf type here, asmio.assembly. So this will create your asmio.o object file, which is used along with your assembled assembly code ran by driver.c. So again, let's look at that here. Okay. So if you remember last time, our assembler in Linux does not put or prepend underscores on C labels. So this means our labels to C labels can be anything, right? But labels can also be used in functions, which is like the identifier or the name of the function. So for example, we have scanf here. So it says define underscore scanf. So this defines sort of a label with this value. So we are saying that underscore scanf now means scanf. This is for elf type. Now, why does your ASMIO dot assembly do this? This is just for uniformity, because remember, if we are using um, Windows, we need to prepend with underscore in order to access functions or labels in C. So that is why if we are using Linux, we are redefining, for example, or like just retranslating scanf into underscore scanf. For Whatcom, we are not using this, but just to see here, no, it is also saying that your scanf underscore, I think Whatcom appends an underscore, not prepends an underscore to your C labels, puts underscores at the end of labels here. So it changes the reference to your scanf to an underscore scanf. This is just for uniformity's sake, which we will see later. So yeah. So if we have defined elf type, which we use sa Linux, then our underscore scanf is actually just scanf. So whenever we use underscore scanf in the code here sa assembly.io.o, it just means scanf because your Linux C compiler does not prepend underscores. Okay, questions about this? Confusing ba? Okay pa man? Sige, we will proceed with some displays here. So we have more definitions here of labels. So we have int format, which is db. So this is a bytes directive. Basically, this is a string. So it says %i and then terminated. This will be used for printing objects, not objects, printing strings in the integer format. This can also be used in your scanf. Later on, we will see. And we have string format, which is %s. When we do dump regs, we also have this register format. So this will have a lot of things in here. Madam siya nga DB declarations, and then this will just dump your register values. And we have also other directives here, no, for directives and labels for strings that we normally use for printing. Okay? Sige. Next, we have your text segment. So your text segment, this is where most of your code, assembly code is put. So we have another definition here, if def object type. So if we are compiling with obj type as an option, it will use this. But since we are doing elf type, we will use this. So segment.text siya instead of segment text public align, yada yada. So here, no, segment.text, and then we declare some things, global read int, print string. So this is so we can use it in our other assembly modules, especially our main assembly or your ASM underscore main. We also have more global stuff here, and we have extern underscore scanf underscore printf get car and put car. So you see here, no, naka underscore scanf na siya, even if we are doing this or compiling this or assembling this rather in Linux. So underscore scanf, because this actually means if you're using elf type, just your scanf. So though mag-switch lang siya, substitution, something like that. Okay. So extern just means it is a function outside of this assembly file. Global means that these functions or labels can be used outside of this assembly file. Sige. Okay, let's take a look at read int. I think this is the only one we'll be looking at for LEA, no, or for your load effective address. Sige, I'll just tab this in para clearer siya, makita. Oops. Here. And then okay. Okay, so let's look at this function called read int. So this is what we use in your assembly instructions for getting input from the user, especially your integers. So first we do enter for 0, meaning we are allocating 4 bytes for a local variable into the stack. And we are pushing the value of EBP as well. And then we say push A. This will be pushing the values of the registers to the stack. And then we have here push F. Push F, we haven't discussed this yet, but push F just pushes the value of our flags register. So we can, so if there are changes in the stack and changes in the flags register rather later, pwede ta siya ma-restore with a pop F command. Okay, so this is the main part of our read int subroutine or subprogram. So the first call is, or the first instruction is LEA EAX EBP -4. So again, when we are using LEA, we are taking the address of a value. So the first argument is the destination. So in this case, we are putting it into our EAX or extended AX register, and the address will be taken from EBP -4. Now this has braces, right? Because we want the value. We want to put the value in here so that our LEA, our load effective address, will take the address of that value. If we put EBP -4 here, for example, this will run into the same error as move EAX EBP -4, where EBP -4 here is not a constant. So we put it in braces, and then the value will the address of this value will be stored in our EAX register. After that, we say push EAX. So we are pushing the value of EAX, which was the address of our local variable in the stack. So our stack now looks like EBP, and then local variable, and then EAX. EAX being the address of our local variable. And then we are pushing a dword int format. So what is this int format? This is a label, or label for a data directive. If we remember, it is this. So it is the address of the string %i. So this is used for taking an integer, no, when we are using scanf. And then we do a call to scanf. So it's like saying scanf, and then the first, since the arguments are pushed in reverse, no? So the last push argument is the first argument in the function call. So it would look like scanf %i, and then we are pushing next is EAX. So this so sa scanf, no, this requires the address. This requires the address of where we will put the integer taken here, integer format. We will store it into the address of the variable where we want to store that value. So in this case, we want to store it in EAX, but EAX is just a pointer to our EBP -4 na value. So then, when we enter something here, EAX, it will be stored in your EBP -4 local variable and not in EAX directly, because scanf requires an address and not a value. Address to store na siya. That's why usually, diba, when we call scanf sa C, if we have integer I, like int I, for example, if we want to store it in int I, we say &I, right? To get the value of I, and not to get the address of I rather than the value of I, because we want to store the value taken from the user %I here into your integer I. So that's the same thing with EAX. So EAX contains the value, or not contains the value. The value of EAX contains the address to your EBP -4 local variable. Okay. There's a chat. So ASMIO is actually uses the C function outside Abixer. ASMIO do the IO functions on its own. Yes, ASMIO will be interfacing with C most of the time. This is used, so your ASMIO is used for like easy interfacing with C. So we don't have to call the C functions and push values in the stack ourselves. It is done so that it is easier to code in assembly. But yes, will there be any performance issues by this? There might be, yes. However, since this is like an introductory course to assembly, then that is why it is made like easier when we first started. But usually, when we are interfacing C and assembly, assembly is used to perform short but highly optimized sub programs or subroutines. But this one is used just for so we could code in assembly easier. So we're just like building knowledge first, and then later on you can use it. You can apply it for something else. Okay. Any more questions with Leia? Or after, sige, we'll finish discussing this code. Then, we then have pop ECX, pop ECX. So what this does is actually just popping the values that we have pushed into the stack now. Mainly that is your dword in format and your push EAX, your EAX value. So these ones are cleared from the stack. And then it says pop F, which pops the flags register, restoring its value. Pop A pops the registers that we have pushed into the stack, so retaining their value. And then we say move EBP minus 4, or the value of EBP minus 4, which was now the input from the user, back to EAX. So here, EAX here, the value is the address of EBP minus 4. Now here, the value of EAX is the actual value of EBP minus 4. And then we say leave, and then return to caller. So now, the output can be taken from your EAX register for your read in. So that is how we apply, or how we use your LEA, or your load effective address, or your LEA na command. So this is, sir, nga may duha ka pop ECX. So remember, pop is pops something from the stack. So it removes the top of the stack now, but your pop instruction needs to have a destination. So that is why usually ECX is used here. I'm not sure why it is ECX commonly, but maybe it's convention to use ECX. But this one actually doesn't really matter, no? When we pop or the destination here doesn't matter much, because we are going to call pop A later. So the value of ECX here will be disregarded, won't be used. So this just pops the values from the stack. Since we pushed 2 values to the stack, we also pop 2 values. This is just the same functionality, no? This is just the same as saying add ESP, right? And then 8, right? So this removes values from the stack. However, pop does have smaller, sorry, pop does have smaller machine code, I think, is what was the explanation sang when we were discussing stack last time. Yeah. So this is just popping the values from the stack. And then pop F, pop A, then the output, which is stored in EAX, and then leave. Okay? Questions? Any more questions? Sige. So the discussion for today will end here. However, some of you, or maybe a lot of you, have deadlines today, right? For your C interface sa labs. So maybe we can use this time for Q&A, question and answer, regarding interfacing with C, how to call your assembly labels in C, which we discussed last meeting, no? But if you have questions, further clarifications, don't be shy to ask it now. We'll be allotting the remaining time for that if we want to revisit calling assembly functions from C. Sige. I'll give you time to ask. Okay. Okay. We have message from Christina. Pwede sir makita paano gina-connect ang sub 5 and main 5 ulit? Okay, sige, we'll rediscuss that. And then we'll address a question from Hamir regarding the stack. Okay, sige, wait. I'll just get your sub 5 and your sub 5 too, and your main 5 too. Okay. Sige, let's start with main 5, no? Here. Okay, so si main 5.c, we have your normal include files here, but we also need your cdecl.h. So this one should be in the same directory as your main 5.c and your other assembly, other needed assembly object files, etc. So we declare first a method prototype, no? When we declare a method prototype in C, we don't declare it with its implementation. This is just like a declaration of a method, which we will be implementing later. So in this case, we won't find the implementation of this method here. Instead, this will be in the assembly file. So it says here, void pre-cdcl. So this is just saying that we are using cdcl as our calling convention. Calcsum is the name of the method or function rather in C, sorry. It gets jumbled with my Java definitions. But anyway, this one asks for an integer and an integer pointer. Okay. And then when we look at our C code, we will look at the definition of this function later sa assembly. When we look at the C code, this is just a print, a scanf, etc. And then we call calcsum here. So n, and then we are passing the address of sum since this requires a pointer. So number pointer siya, or integer pointer rather. So we are passing the address of sum. Okay. So again, remember that these are pushed into the stack in reverse. So see at ampersand sum, which is the address of sum, is pushed first and then pushed second cn. Okay. So yeah, let's look at your sub 5 assembly. So see sub 5. Okay. Here. So notice that in sub 5, we are not declaring the label ASM underscore main because we are not running your assembly main module. In this case, we are just running a part of our assembly code or yes, a part of our assembly code but is not the main assembly na label. In this case, ang label niya is calcsum because this is also the name of the function. Global here just says that this can be used outside of the assembly file or the assembly object so that we can call it from C. So calcsum here, global calcsum, and then this is the start of our calcsum na function. So the first thing we do here is enter 40. This allocates a local variable to the stack. We will be using that for the sum. Sorry. Okay. And then we have push EBX. This is important because we do not want any changes for our EBX. That is part of the calling convention. We don't want our EBX to be changed. So we store the value of EBX before we do something about it. Okay, and then the rest of here is just calling your the function for for calcsum, no, which takes EBP minus 40. This clears the sum or the local variable. Dump stack here is just for debugging to display the values of the stack. And then we have move ECX1. This is for the counter. And then we count from ECX until EBP plus 8. This is your N. Because if we go back to main 5.c, this is EBP plus 8 because it is pushed in reverse, right? And this is EBP plus 12, your address. Okay, going back to sub 5. So if it is, this is jump not less than or equal, meaning if nag-greater na siya, we end the for loop here. What we do sa for loop is we just add EBP minus 4. This is our local variable for the sum and ECX. So this will loop, right? So if we enter 10, that's 1 plus 2 plus 3 plus 4 until plus 10. And it is stored in your local variable EBP minus 4. You're incrementing ECX after that, and then that will just loop. Okay? After that, we have the 3 lines here. Move EBX, EBP plus 12. Again, this is the address for our sum na ginpasta like here. This is the address of our sum. So in our sub 5, we are moving it to EBX. The value of EBP plus 12 is the address of our sum integer. And then we say move EAX EBP minus 4. So we are moving the value of our local variable sum and local to EAX. And then finally we say move in braces EBX EAX. So this is in braces because the value of our EBX is the address of our sum. So we dereference EBX and move the value to that. So now the value of our sum is in our sum integer here, this one. Ari na siya di sa sulod. Okay? And then we pop EBX. So we restore the value of the EBX that we pushed here earlier. And then we say leave and then return. Return returns to the caller, which is your calc sum here. So print. So when we print sum, the value is already in your sum because this is passed through reference. Now we can alter this. We can alter this main 5.c in a way that we do not need a pointer to the sum. We can restructure this in a way that your calc sum will return the sum, the actual sum, and not pass by reference. So to do that, we do int earlier this was void, so doesn't matter. The return value doesn't matter for the function, but now we have int, so we have a return value that actually matters for our function. So if we have a return value that is integral or a pointer, we can store it in EAX, and that will be used by your C depends sa calling convention. In this case, CDECL. We will take the output or the return value from our EAX register. So in this case, we do, so same lang, scanf here, we get the value of n, and then we print sum. The only change here is that we have sum equals calc sum n. So the return value of our function calc sum n is stored in sum, and it is no longer passed by reference if like here, no? It is return value na siya. And then our calc sum, instead of int and int pointer, since we are no longer passing the reference of our sum, int na lang siya. So this is the previous one, int and int pointer. The changed code, int na lang siya. So you're just passing n here. Okay. If we look at the changes to sub 5 underscore 2, We still have your push EBX. Very important, no? Same lang siya. And then I commented this part of the code, which says move the word EBP minus 40, since we do not have any local variables declared here, because we will be storing the sum in EAX anyway, so we do not need a local variable for this. And then I say XOR EAX EAX, because we are clearing the value of EAX. This will be preparation for the sum. Moving forward, ECX is equal to 1. This is just I in the pseudocode, no? It starts at 1. And then this is our for loop. So compare same as earlier. If our ECX is greater than our EBP plus 8, EBP plus 8 meaning n here, no? Ang aton nga pushed na parameter to the stack. JNLE and 4. Okay, so ma-end lang siya if nag-equal na. Or greater, rather. And then we say add EAX, ECX. So the difference here with sub 5 ASM earlier is that we are adding, our destination is the local variable. Now we are just using your EAX. So add EAX, ECX. So this will be our sum. Okay, so after that loop, I commented this out because we are no longer using our pass by reference. The return value is in EAX anyway, so we don't need these lines of code anyway. And then we say pop EBX to restore the value of EBX. If you really look at this, this is not really needed, but it is just nice to have, just to have an insurance, know that our EBX retains its value before going back to our C code. So pop EBX, leave, return. So if we go back here, so main 2, the return value is in EAX, so the sum is assigned to the sum and then printed lang. So that is how your main 5.c and your sub 5.c. Okay. Any questions about that? Sige. Sige, let's address ang question ni Hamir. Pwede ka rediscuss ang stack. Late kami last time. So which part of the stack do you want to be rediscussed? Because there's this goes way back. I'm not sure which part of the stack you want to be discussed. EBP and addresses, sir. Sige. Kung WSL. Hello. Okay, sige. May paint ako dire. Kasi I don't have a whiteboard. So sa paint na lang kita, Nay. Okay, anyway. So C stack, the common representation of our stack, right, is from top to bottom. But our sa assembly, we represent the stack as like a top to bottom or bottom. So bottom siya push. So imagine that you are pushing from the bottom. So push is here, that direction, and pop is here, that direction. Okay, so your question is EBP and addresses. So whenever we have call, the call na instruction, it will push the address or the return address to the stack. This is the point of your code where you will be returning. Sige, let's find an example. Sige, sa sub 5 early, no, not sub 5. Sa main 5 earlier. So when we have a call, a method call like this, the return address is pushed into the stack. The return address is this one, where the execution will return to. So usually it is after the function call. So that will be pushed. Where's your text? Pushed here. Return address. Zoom ko lang para. So after the return address, usually sa function declarations or sa function implementations, rather, we have the enter and then something, the parameters here. The first parameter is the byte allocations. So this one pushes EBP first. So the first thing that enter does is pushes the EBP value. So EBP is now here. This is the value of the EBP before the changes. And then after that, we say, after this, no? So this is still in enter. We say EBP is equal to ESP or move EBP ESP. Move EBP ESP. Since our ESP stack pointer differs every time, we store the value of that stack pointer at this time to EBP para maging anchor siya. So whenever ESP changes here, doesn't matter, we just refer to EBP because ESP will change. Then after that is if we have 40, meaning we are allocating memory for a local variable. So local variable here. Local variable. There. It doesn't mean that this is all 000. So that is why usually you need to clear the local variable. Okay, so that is the usual thing if we don't have parameters sa function calls. If we have parameters sa function call, for example, sa main5.c, like here we have two parameters, right? So n and ampersand sum, or the address of sum. So this will be pushed to the stack before the actual return address. And this is pushed in reverse. This one is pushed first and then n. So if we look at that sa stack, it will look like this. First, address of sum variable, and then we have n here. And then we will have your return to caller address. Okay, and then we say enter. So the first line of your subroutine or subprogram is usually always enter and then local variable declaration or reserving space for your local variable. So enter again pushes EBP, and then we say move EBP ESP. Okay, so your EBP is here, pointing here. So your EBP is pointing here. So that's EBP. Okay, and then this will be your local variable. Now, when we are accessing the parameters pushed into the stack, this part will always be EBP plus 8. EBP plus 8. And then the second variable will always be EBP plus 12. Because we are moving plus 4, right? So this is EBP plus 0. This is EBP plus 4. So we don't touch EBP plus 4 because that's the return address to the caller, right? And then your local address, local address is, the first one is always EBP minus 4. There. Okay na? Sa stack? Any more questions? If it's still hard to understand, no, I will be in the faculty room. If you want to consult, later, siguro around 11:30 until end of day, around 5:30, if you still want like an explanation for this. How about the sub-program addresses? Sub-program addresses, okay. So usually naka-label na siya. We have a label for this. So this is an address. We do not need to calculate the address of this, however, because this has a label. So si assembly na bahala or si linker na bahala mag-supply for that address when we call it. We do not usually push the address of the subprogram. It is usually the address, the return address to the caller, because we need an anchor. No, we need a point where we need to go back. Usually the destination is determined by the linker, but we need the return address to go back. We need to push it. Bale, basically, ang address ng subprogram is determined by the linker whenever you call the function or the label of that subprogram. So this one is a call to calc sum, right? So si linker na bahala mag-search for the address of that, which is this. Well, this. Sa mga EBP minus 8, like deeper parts of the stack, EBP minus 8 is actually the top of the stack. So when we are doing minus, it looks deeper, no? Because the representation, it looks deeper, but that is actually the top of the stack. So when we go minus, we go down here. But in this case, the representation yan local variable is the top of your stack, actually. Because dogin baliskad lang ang stack natin. So for example, you did enter 80, for example, no? This one will allocate 8 bytes of reserved data. So that in that case, you are reserving 2 local variables. So that's local variable 1 and local variable 2. Local variable 2, and this is local variable 1. And this is EBP minus 8. Oh, okay. So code, sir, do we have to push EBX after enter 40, where na siya makita under local variable stack, no? Okay. So if we have this, for example, enter 80, meaning we are pushing, we are allocating 2 variables, local variables in the stack, and then we push EBX, meaning your EBX is after the local variables. So your EBX will be here. And that is, in this case, EBP minus 12. Morning, sir. Ask ko lang kung saan mo i-upload ang lecture slides for today's session. I will upload it later. Pero because I have a meeting to attend sa 9 a.m. So maybe after that, maybe mga 10. What is this? Move ESP EBP. This move ESP EBP, that happens sa leave. That happens sa leave, ang move ESP EBP. This is because we want our ESP, because the dynamics ESP, whenever you're pushing something into the stack, you are you are moving ESP around. So ESP is just a pointer to the top of the stack. So in this case, EBP minus 12 here is the top of the stack. That is also your ESP. We want to do move ESP EBP when we leave, so that here, no, mabalik si ESP on where EBP is. And then it will then pop EBP. So ang top of the stack mo after leave, no, is your return to caller address. Because when we move ESP EBP, it will now be pointing here, kung diin si EBP. And then when we pop EBP, meaning we are removing this from the stack, plus si ESP, ESP is now pointing to your return to caller address. And that is used when we do the return instruction to return to the caller. Okay. Any more questions? Kung i-pop ang EBP, sir, ma-pop man ang ara sa ilalim niya. EBP 4 minus EBP minus 4, EBP minus 8. So usually what happens when we do leave, no, sa leave is move ESP EBP, meaning we are moving our ESP pointer back to EBP, to where EBP was. Okay, so whatever things that are in this part of the stack, madula na ni siya. Well, it's still there, pero our ESP pointer is now pointing here. So ESP, oops, sorry. So after that, no, ESP will now be pointing here, where EBP is. Okay, and then we pop EBP. Popping doesn't concern your EBP. Si ESP lang na ang pointer nga ang gina-concern ni pop. So pops wherever ESP is pointing, because that is the top of the stack. So this one, mag-pop EBP ikaw, i-pop ni ang value ni EBP, and the destination of that usually is EBP. So whatever value of EBP before will be popped here, pop back to EBP para hindi siya mag-change. And then ESP after that will be pointing to your return to caller address na. So you can leave, you can return to the caller address. So wala na ni siya labot, may local variables ka pa dire, doesn't matter anymore. Hindi na ma-access. Yes, there will be a recording. I will upload it later. How are local variables cleaned up? It's not cleaned up. Okay? Ginapabayaan na lang na siya sa stack. And if whenever like a program will use that space, then may values pa na siya gihapon. That is why when we are allocating variables, local variables like EBP, enter 40, we need to clear it, right? Kung gusto ta nga naka-0 siya, we need to move 0 to it para ma-clear siya. So di ma-clear ang memories ng local variables pagkatapos ng pop. Again, that's not the problem of the um, execution or the memory execution. Pwede na siya gamiton sa other parts of your CPU because that's now basically you're giving the allocation of that away because your ESP is moved na, 'di ba? So anything after that, wala na labot si ESP or si EBP or your program execution. It can be used by other stuff that will point to that stack. So hindi mo na siya concern. Sige, may questions pa? Tara na faculty sir, may meeting. Not everyone. Sige, because I might be running a little late na. Maybe we can end this here. If you have more questions, you can ask me siguro around 11:30, no? Sa faculty room. So see you there na lang. Or I'll just message if I'm in the faculty room sa Discord. Okay, so I'll stop it here. See you Thursday. Okay, bye-bye.
Thank you, sir.
Thank you, sir.